Hi. In this video, we're going to take a look at the physics of falling objects. The acceleration that's caused by the pull of gravity is one of the rare examples of constant acceleration. Constant acceleration along the horizontal axis is extremely rare because of forces like air resistance and friction. Even with gravity, though, we have to make certain generalizations, and this is a common theme in physics where we try and understand the most basic situation first before we turn on other things like air resistance. Also, gravity is free, so why not use it? So here in this slide, we talk about the effect of air resistance, acknowledging it, but the piece of paper and the ball, when they're dropped, will have the same acceleration if the air resistance of the paper is reduced. And of course, we also acknowledge the fact that air resistance depends on a number of things, like the shape of an object, the size of an object, and also how fast it's going. So you probably noticed this, that air resistance, when you open up a car window, you can feel air resistance. That's that turbulence that you experience. And it's a lot more when you're going faster. So we're going to just eliminate air resistance from our conversation for right now. So the acceleration that falling objects experience here on the Earth's surface is about 9.8 meters per second. So that means that after each second, our falling objects gain 9.8 meters per second every second, and it just keeps on gaining. So the velocity will increase in a linear way, but the distance falling will not be linear. Looks more like a quadratic, right? So now we can take our kinematic equations and modify them. If we've been using x for left and right, then we can use the letter y for up and down. And we also have to account for the fact that gravity is always downward. So the acceleration due to gravity we refer to as g. And if you've heard the expression pulling g's, that's actually exactly what folks are talking about. They're comparing their acceleration to that of gravity, which we experience on a daily basis. So I'd like to take a look at a couple of examples with the kinematic equations modified for free fall. And you'll notice that the kinematic equations are all the same. They're very similar. We introduce delta y, which is going to be a final y position minus initial y position. And then also, anytime there's an acceleration term, we plugged in minus g. All right, so let's just take a look at a couple of simple examples. Great. So here are a couple of examples. We'll start off with a famous cliff problem where we have someone is dropping a ball off a cliff and the ball hits the ground 3 seconds later. So let's try and use that factor and figure out everything else that's happening. Now, we might as well go ahead and list our variables, right? So we could go initial height and final height, and initial velocity in the y direction and final velocity in the y direction. Obviously, later on, we're going to have things that are moving both in x and in y. Now, the acceleration, well, we already know gravity is 9.8 meters per second squared. And so I'm just going to skip over to t. And then we'll go back and figure out what are things that we know so far. Now, the initial height, we could say is 0. Or we could claim that that's what we're looking for. And so if we claim that the initial height is 0, then the y part, which would be the height of the cliff, that would be what we're looking for. But if we set initial height to be what we're looking for, then that means our final height is equal to 0. Now, both of these are legit because the delta y is still the same. That's just a choice of reference points. So it doesn't matter whether this is 0 and this is a negative number, or this is 0 and this is a positive number. Now this object is just let go, so we're going to assume that it simply falls. So that means that the initial velocity is 0. And the final velocity we don't know, but the time it takes to hit the ground we do know, and that's 3 seconds. Okay, so now we think about those kinematic equations we've been using and which ones are going to be the go-tos. So let's suppose we're looking for our y value and we know what time is. So our equation of motion, we can go with equation number 1, whoops, q1, which looks like this. So y minus y0, on the chart it says delta y, equals v0y or vy0, doesn't matter, times time, minus 1/2 gt squared. And now it's time to put in some numbers and we'll see what's cooking there. So I'm going to use this scenario, but it doesn't really matter. And so y is going to be the thing I don't know. And then initial velocity is 0, and 0 times any number is still going to be 0. And then minus 1/2, and now put in the number for gravity, and that's 9.8. Not negative 9.8, because we already took care of the minus sign. And then 3 squared. So this is great. We don't have any large number of variables to keep track of. So we'll bring in our trusty calculator in and see what's up. So 1 divided by 2 times 9.8. I don't really have to worry about the minus sign, times 3 squared. Okay, 44.1. So it's 44.1 meters with a minus sign, meaning that the ball winds up 44.1 meters below where we started. And if we wanted to continue and find out what the final velocity is going to be, then let's see, I'm trying to remember which equation that is. I think it's the yeah, I think it's the third one. So velocity in the y direction is equal to initial velocity in the y direction minus gt. So this is actually pretty easy. Yeah, and we notice that this is going to wind up with a negative number because our initial velocity is equal to 0. Now 3 seconds of free fall is actually quite a lot. So 29.4 is going to be on the order of like 75 miles an hour. It's pretty fast. And the negative sign indicates it's traveling downward. Okay, well, let's use this as our inspiration for looking at a throw-up problem. And in our throw-up problem, we'll take our friend, we'll give him something to throw. We'll give him a good wind up here. We'll make it a different color just so this person doesn't accidentally throw their hat. And we'll assume that this is equal to 0, that where it starts from is equal to 0. Also, this is assuming we know it's going to take a force to throw this ball in the air, and the person's hand is going to be in contact with the ball for a little bit. But that's all stuff we're going to hold off talking about right now. We just want to look at the effects of gravity. So our ball is going to go up and reach its highest point, and then come back down again, and then hit the ground. Let's pause for a second and think about the direction of the velocity here. So this velocity is going to be on the way up. But at the highest point, the velocity equals 0 because we're changing direction. And then on the way down, the velocity is downward, of course. Now, when it comes to acceleration, remember there are three ways that you can accelerate: speeding up, slowing down, and changing direction. We haven't really seen a lot of examples of changing direction, but this is one of them. So let's take a look and see what's happening with the acceleration. So the acceleration is downward. And since the acceleration and velocity oppose each other, that's why it slows down. And then over here, the acceleration is downward. That's how come it picks up speed. So this is slowing down. This is speeding up. What's happening here? A big misconception is to say that the acceleration is equal to 0. And that's not true. So I'm going to put a big fat cross out through it. No, the acceleration is still down. This is the acceleration caused by gravity. So writing acceleration equal to 0 at the top has a couple of major problems. Number one is that why would gravity change just because you threw a ball in the air? That doesn't make any sense. And number two, if the acceleration was 0, then it's not coming down. It's just going to stay there. Acceleration 0, velocity 0, that's called stopped. That's not coming back, right? So anyway, good for us to think about. Let's go ahead and provide some extra variables. And in our throw up problem, let's, just for fun, let's use our initial velocity in the y direction to be positive 29.4. Just so we can wind up drawing some interesting parallels between these two, right? So what if we had like a perfectly elastic collision with the ground, and then it bounced off the ground at the same speed that it hit at? And what kinds of things are we looking for? We might find the time in air. We might find the maximum height. In my teaching career, max height is actually evolved into a character. So special agent max height. Okay, great. And let's also further break it up into two pieces, because the max height and the time in the air are actually two different problems. So time in the air is up and down, but finding max height is up or down, but not both. So the conditions that exist for that motion are either on the way up or on the way down. So let's do that. Let's go up and down. And let's see what that looks like. So the conditions for up and down, we can go ahead and write down what our variables are. Well, up and down has the unique quality where it's going to start off at 0 meters, and then it's going to end up at 0 meters. And the initial velocity, we said we're going to use the opposite of what we solved for in the last problem, just to draw some parallels. Question mark here and question mark here. So this would be how fast it's going just before it hits the ground. And then this is the time in the air, which we're looking for. So as I'm scanning, I want to find an equation that does not have final velocity in it. And that sounds like this one. Number one again. Keep up with my color coding. So y minus y0, delta y, is equal to v0y t minus 1/2 gt squared. And the only thing we don't know is time. So both of these are 0. And the initial velocity is equal to 29.4 t minus, and 1/2 of 9.8 is 4.9. Right, how do we solve that? Well, we're going to factor out a t. I'm kind of running out of space here, but I think I can squeeze it in. What we know is that we're going to have 4.9 t squared equals 29.4 t. So one of the t's is going to cancel. The math people don't like this. Oh, you have to include the possibility that t is equal to 0. I don't know which math teacher that was, but that was somebody. And 29.4 and then divided by 4.9. And that's 6. On the nose. Now, if we come back here and take a look, right, this was after falling for 3 seconds. So it turns out that on the way up, it takes 3 seconds, and on the way down, it takes 3 seconds. So it's on the way down, it actually looks exactly like this. So now to find max height, special agent max height, we need to consider either up or down. And I choose down because I think it's going to be a little easier. Initial height, final height, initial velocity in y direction. Remember, we're going to go from here downward. Final velocity, time. Okay, so initial height, we don't really know what this is, but that is special agent max height. Special agent max height. And then our final height is 0, and our initial velocity is 0. The final velocity, we don't really know that yet. We have probably a pretty good guess. But for the time, I'm going to take total time divided by 2 because there's nice symmetry in this problem. And so that's going to be 3 seconds. And now you realize that's actually exactly the same as this problem over here. But let's go ahead and do the math out because practice is very important. Okay, here come the numbers. So it's actually y0 is what I'm looking for. And 0 times anything is still 0. And then minus 4.9 times 3 squared. But deja vu, I think I've already done that math before. I did it over here. 1/2 of 9.8 is 4.9 times 3. Yeah, so the initial height is 44, or max height. Whoops, I kind of forgot them. There we go. Right, so there's a lot of symmetry here. On the way up, looks very much like the way down. The main difference is that on the way up, the velocity is upward. It even starts off at the same speed that it lands at. So plus 29.4 over here and negative 29.4 over here. Okay, well, I hope those examples help you get started on the homework. I'm going to post a couple of more challenging ones tomorrow.